Turning to slide 18, we're going to take a look at the automatic multi-step approaches, covering both distal outcomes and covariates. So on slide 19, the auxiliary option is introduced. So it's automatic, which means that you can do a single run to analyze the measurement model while also adding the full model variables using this auxiliary option. And you have distal outcome settings and covariate settings for this. So the distal outcome settings are variations of 3-step that I mentioned on slides 6 and 9 earlier, and variations on BCH. For covariate settings, we only have a 3-step variation called R3-step. There are many other settings for the auxiliary options that we have worked with in the past and investigated in the past and discussed in WebNote 21, but they're no longer recommended by us. On slide 20 then, we're focusing on the automatic approach for distal outcomes. And here is the list of the different distal outcomes, the acronyms for those. And we're going to take a look at them in more detail further on. So let's focus on the pros and the cons of this automatic approach vis-a-vis the manual approach. So the pros of this is the convenience of doing a single run, and no need to save class probabilities and fix logits from the first to the last step, which we do in 3-step analysis, or save the BCH weights that we use in the BCH approach. So that's the convenience. And the limitation is that the distal outcomes cannot also be regressed on covariates, which you may want to do in many cases. So for that you need the the manual approach. And with several distal outcomes, the analysis is not done jointly for all of the outcomes, but one variable, one distal outcome at a time. So a missing data methodology does not come into play. And that's an advantage of the manual approach once again. An exception to that is that typex imputation analysis can be used. So data type equals imputation, which is described in the manual section where I talk about imputation matters. And another disadvantage is that only one latent class variables can be handled. The LCA, of course, only deals with one latent class variable, so that's not a limitation in that case, but it would be in the latent transition analysis, for instance. So slide 21 then talks about the automatic approach for covariates. So pros and cons of the auxiliary are 3-step. There's only one approach for that in Mplus. Pro, again, is convenience, single run, no need to save C probabilities and fix the logits. Limitation, observations with missing data on one or more of the covariates are deleted, just like in regression, with the exception of typex imputation. Direct effects from covariates to latent class indicators, differential item functioning or measurement non-invariance cannot be included. And actually that's covered especially in Webtalk, Webtalk 9. And again, only one latent class variable can be handled. So let's take a look at the distal outcome version in an actual analysis here using automatic multistep. So let's take a look at slide 23, where the full model includes distal outcomes Y added to the LCA measurement model. So we have 3 distal outcomes here. Y1 is continuous, Y2 binary, and Y3 ordinal. So we're going to use the automatic approaches of auxiliary BCH and BCHC, where C stands for the categorical cases, which covers both the binary and the ordinal case. So here's the input for auxiliary BCH. It's the same data set, distal.dat, that we talked about before. And the use variables are still U1 through U6 here, except that we also add the auxiliary statement where we want to bring in the full model variables of Y1 through Y3. Y1 is continuous, so we use the BCH approach. Y2 and Y3 are categorical, binary and ordinal, so we add C to that. It's also possible, as I say here, to mix it up, to have BCH options mixed with 3-step options, and the different variations of that. Now, for this case, we still then have the typical mixture analysis specifications as before, but no model command needed here either, because the threshold probabilities vary across all classes by default. So this is all you have to say. So we do step 1 using the U1 through U6, and the full step, the final step, full model final step as the 3 Y variables. And then Mplus provides tests for these distal outcomes. Y1 is continuous, so we test mean differences across the classes. First, we note that the number of observations deleted for this variable is 178. So Y1 has missing data, and the ones used are therefore 822. So we lose some people there. And this is what you can avoid when you do a joint analysis of all 3 Y variables using the manual approach. But often the drop is not that big. And the means then of the classes are listed here, the standard errors. And then we also provide a chi-square test of differences between these 3 means overall and for each class versus every other class. And p-values are significant here, so there are significant differences across classes in the Y1 outcome, distal outcome. For the binary Y2, we give several statistics. We give the probabilities in the different categories of the outcome and for the different classes. And we give the standard errors of those probabilities, but also, more importantly, give the odds ratios. So an odds ratio, as we know, is a measure of a relationship between 2 variables. So what are the 2 variables? Well, it's the distal outcome with its 2 categories and the latent class variable. And we compare then each class to the last class. So each category here is the second category compared to the first, and the classes are compared to the last class. So the odds ratios be 1 for the last class here. So for instance then, if you look at class 1, you have the odds here of being in class 2 versus 1 as this 0.676 divided by 0.324 for class 1, and for class 3 it is 0.437 divided by 563, so much smaller ratio, much smaller odds rather. And if you take the ratio of the first to the last, you get this odds ratio 2.688. You may want to try that. And you also get a standard error for that, but more importantly, you want to work with these non-symmetric confidence intervals for odds ratios. So for instance then, for the category 2 of class of the binary outcome, you have a confidence interval that goes from 1.7 to 4.0. So it is not including the neutral point of 1, which means it's significant. So the odds rate, the y2 is significant differences between class 1 and class 3. For the class 2 versus class 3, you have a confidence interval that includes 1, so this is insignificant. And we also give chi-square test of these differences overall with p-values, and we see that all differences are significant except class 2 versus class 3. And you can see that already in the probabilities here. The ratio of these probabilities are fairly similar and therefore cause the insignificance. So in conclusion, the answer to the question, does the latent class variable have an effect on y2? Well, when we compare class 1 with class 3, the answer is yes, because the confidence interval does not include 1. But when we compare class 2 to class 3, the answer is no. We have an insignificance there. Confidence interval covers 1. And this is also seen in the chi-square test section at the bottom, where we test differences in probabilities. We have an overall test, but we were looking at the class-specific test, and we see the significance here, but not for class 2 versus class 3. Degrees of freedom is 1 for those class-specific comparisons. Turning then to slide 27, we look at the ordinal y3. So here we have a 3-category distal outcome. So the question is, does the latent class variable have an effect on y3? So let's take a look at the details here. So now we have 2 odds ratios per class. For example, for class 1, we can consider the odds both for category 2 versus 1 and category 3 versus 1. And we can compare those 2 odds with the odds that we get in class 3, and thereby get odds ratios 0.998 to 1.033. Now, if you look at the confidence intervals, you see that all of the odds ratios here include the confidence interval for the odds ratios include 1, and therefore there's nothing significant. So no effect of the latent class variable on y3. And that's because of the population values that we used for the Monte Carlo simulation that generated the data. We see then that if you look at those in the appendix, you see that the population values differ much less for y3 than for y2. For y2 we did find some significance, but here for y3, for those differences, we don't have enough power to detect the differences even at the sample size of 1,000. The insignificant result is also seen in the chi-square testing at the bottom of this slide, where the p-values for the class comparisons are not small. So we can't reject that they are equal. And note here now that we have 2 degrees of freedom for the class differences. That's because we have 3 categories for y3. We had only 1 degree of freedom for y2 because it was binary, but now we have 3 categories for y3, so that when you do testing of probabilities, you get with 2 categories, you have 1 probability to test because the probabilities add to 1. With 3 categories, you have 2 degrees of freedom because those probabilities add to 1 as well. Turning then to covariates on slide 28 for the automatic approach. Slide 29 gives the model. We're going to work with 3 x variables and illustrate auxiliary or 3-step. So on slide 30, you have the same distal data set rather, And the use variables are still U1 through U6, corresponding to the measurement model of step 1. And the outcomes, or rather in this case the covariates, are x1, x2, x3, and we use the R 3-step regression, 3-step C on X regression approach. And we note here, for instance, a little detail: x1, x2, x3 are not consecutive names on the names list. The x1, x's, and the y's are mixed up here, so you better specify them without the list function. And you just note that this parenthetical R 3-step can alternatively be placed after each variable. And again, no model command needed. So this is all you need to do for the auxiliary R 3-step. Now, with R 3-step, we have list-wise deletion applied to the auxiliary variables. And to avoid that, you can take the tack of data imputation, followed by analysis with type equals imputation, which I will illustrate in the manual approach section. The number of deleted observations again here is 332, and the ones used 668. So you lose quite a big chunk of data in this set, in this example, with the distal.dat data set. In most cases, or in many cases, you don't have that missing data on X. And it's not worth it to get into imputation matters. So here you have the results for auxiliary R 3-step. So you have 3 classes. So you have C#1, class 1 on the 3-axis, and class 2 on the 3-axis. Whereas the coefficients, the logit coefficients, are 0 for the last class. So we are comparing to the last class as usual in this multinomial logistic regression of C on X. So what we present in the output, this output section, is odds ratios. So these are odds ratios given here, estimates, and we focus on the 95% CI, the non-symmetric confidence interval, and look at the significance of that. So here it looks like X1 has a significant effect, and X2 does, and X3 as well. This is regarding class 1 versus 3. But for class 2 versus 3, you include 1 here. So that's insignificant, this is significant, and this is insignificant.